3.5 Derivatives of trigonometric functions. The outline of this video is as follows. We will begin by establishing the foundational rules for differentiating the two primary trigonometric functions. First, I will walk through the formal proof, starting from the limit definition of the derivative to find the derivative of the sine function. Next, we will use a very similar approach, along with an angle sum identity, to derive the corresponding rule for the cosine function. With these two key results in hand, we will then practice applying them to more complex expressions. I will show you how to combine these new rules with the product and quotient rules to differentiate functions that involve both trigonometric and algebraic parts. To conclude, we will explore a powerful real-world application by analyzing simple harmonic motion. This is the mathematical model for oscillating systems, such as a weight bouncing on a spring, and it provides a great example of how these calculus concepts describe physical phenomena. We are about to explore the derivatives of trigonometric functions, which are essential tools for understanding anything that changes in a repeating cycle. Many processes in nature are periodic, from the oscillation of electromagnetic fields to the regular rhythm of a human heartbeat. The functions sine and cosine are our primary tools for creating mathematical models of these repeating patterns. For example, we can use a cosine function to model the height of an ocean tide over a 24-hour period. But to analyze the dynamics of that system, such as finding the exact moment the tide is rising fastest, we need to calculate its instantaneous rate of change. This is precisely what the derivative gives us. Therefore, learning to differentiate these functions is the key to unlocking a deeper, more dynamic analysis of the periodic world all around us. Now I will show you how we find the derivative of the sine function, a crucial tool for analyzing anything that changes in cycles. We start with the formal definition of the derivative, which involves the limit of a difference quotient as ACH approaches 0. The key step is to use the angle sum identity for sine, which let us expand the term sine of the quantity x plus h. After rearranging the terms, the problem simplifies down to two fundamental limits we have already established. The limit of sine h over h as h approaches 0 is 1, and the limit of the quantity cosine h minus 1 all over h is 0. Linking in these values gives us our final answer. For instance, at x equals 0, the sine curve has a slope of 1, which is exactly the value of cosine at 0. It is very important that these rules apply only when x is measured in radians. The simple takeaway is that the derivative of the sine function is the cosine function. Now that we know the derivative of sine is cosine, we can see how it works with the standard differentiation rules we have already learned. This is important because it let us handle much more complex functions. Let us take the product rule as our main example, with the function y equals x squared times sine x. To find the derivative, we follow the rule. We take the first part, x squared, and multiply it by the derivative of the second, which is cosine x. Then we add the second part, sine x, multiplied by the derivative of the first, which is 2x. The difference and quotient rule examples on the slide follow the exact same pattern, just with their own specific structures. The key takeaway is that you do not need to learn a new process. You just plug the new sine derivative into the familiar rules. Now that we have the derivative for sine, we will find the derivative of the cosine function, which follows a very similar process. We begin with the limit definition of the derivative and apply the angle sum identity for cosine. This allows us to rearrange the expression and use the same two fundamental trigonometric limits we saw earlier. The figure here helps us visualize this result. The blue curve, y equals cos x, has its slope at every point described by the red curve, lie prime equals negative sin x. For instance, at x equals 0, the cosine graph is flat, and its slope is 0, which is precisely where the red negative sine graph crosses the x-axis. The most important detail to remember is the negative sign that appears in the result. The derivative of the cosine of x is negative sine of x. Now that we have the derivative for cosine, I want to show you how it combines seamlessly with the sum, product, and quotient rules we already know. First, for a simple sum like 5x plus cosine x, we can differentiate each part separately, which gives us 5 minus sine x. For a product like sine x times cosine x, we apply the product rule. The first function times the derivative of the second, plus the second function times the derivative of the first. This results in the expression cosine squared x minus sine squared x. Finally, for a quotient like cosine x over the quantity 1 minus sine x, applying the quotient rule and simplifying with a trigonometric identity gives us the clean result of 1 over the quantity 1 minus sine x. The main point is that this new rule for cosine works exactly as you would expect within our existing differentiation framework. Let us see how we can apply derivatives to understand physical movement, using a classic example called simple harmonic motion. Imagine a weight bobbing up and down on a spring. Its position at any time t can be described by the function s equals 5 times the cosine of t. This means it oscillates between a position of 5 and negative 5. To find its velocity, we simply take the derivative of the position function, which gives us v equals negative 5 times the sine of t. To find its acceleration, we take the derivative one more time, which gives us a equals negative 5 times the cosine of t. Notice that the acceleration is just the negative of the position function. This means the restoring force is always pulling the weight back towards its central rest position. So by taking successive derivatives, we can build a complete picture of the object's motion from its starting position alone. Now let us analyze the motion of this spring to see what the equations tell us about its physical behavior. The position function, s equals 5 cos t, shows the weight oscillates between negative 5 and positive 5, giving it an amplitude of 5 and a period of 2 pi. The speed, which is the magnitude of velocity, is greatest right as the weight passes through its central rest position, where s equals 0. Conversely, the speed drops to 0 at the very top and bottom of its path, where s is plus or minus 5, as the weight momentarily stops to reverse directions. Most importantly, we see the acceleration is negative 5 cos t, which is exactly the negative of the position s. This relationship, where acceleration is proportional to the negative of displacement, is the defining characteristic of simple harmonic motion. The key takeaway is that the restoring force is strongest at the points farthest from the center. Now that we know the derivatives of sine and cosine, we can find the derivatives for the other 4 trigonometric functions, as they are all defined using ratios of sine and cosine. We derive each of these rules by applying the quotient rule. For example, the derivative of tangent x is secant squared x, and the derivative of secant x is secant x times tangent x. The remaining 2 are the derivative of cotangent x, which is negative cosecant squared x, and the derivative of cosecant x, which is negative cosecant x, times cotangent x. You may notice a helpful pattern. The derivatives of the 3 CO functions we have seen, cosine, cotangent, and cosecant, all have a negative sign. This pattern can make the rules easier to remember. Learning these 4 new formulas completes our set of tools for differentiating the 6 basic trigonometric functions. Now let us find the derivative of the tangent function by combining rules we have already learned. The key is to first rewrite tangents of x using its definition, which is the fraction sine of x over cosine of x. Since we have a fraction, I can apply the quotient rule, which results in the expression you see here. The next step is to substitute the derivatives we found earlier. The derivative of sine is cosine, and the derivative of cosine is negative sine. After substituting, the numerator simplifies to cosine squared of x plus sine squared of x. This is a great example of how other math rules appear in calculus, because the Pythagorean identity tells us this numerator is exactly equal to 1. This leaves us with 1 over cosine squared of x, which is the definition of secant squared of x. So the important takeaway is that the derivative of tangents of x is secant squared of x. Let us practice finding a higher order derivative by calculating the second derivative of the second function. We begin with the first derivative of secant x, which we know is secant x times tangent x. To get the second derivative, we must now differentiate this product, which requires us to use the product rule. Following the rule, we take the first term, secant x, and multiply it by the derivative of the second term, tangent x, which gives us secant x times secant squared x. Next, we add the second term, tangent x, multiplied by the derivative of the first term, secant x, which results in tangent x times the quantity secant x tangent x. After simplifying both parts of the sum, our final expression is secant cubed x plus secant x times tangent squared x. This example shows how finding higher derivatives often involves combining several differentiation rules. Let us bring together all 6 of the trigonometric derivative rules we have established, which are fundamental for analyzing periodic phenomena. First, we have our base pair. The derivative of sine of x is cosine of x, while the derivative of cosine of x is negative sine of x. Next are the tangent and secant derivatives. The derivative of tangent of x is secant squared of x, and the derivative of secant of x is secant of x times tangent of x. Finally, we have the derivatives for their CO functions. The derivative of cotangent of x is negative cosecant squared of x, and the derivative of cosecant of x is negative cosecant of x times cotangent of x. A helpful pattern to remember is that the derivative of every cofunction, which includes cosine, cotangent, and cosecant, introduces a negative sign. Mastering these 6 rules is essential for working with any model involving oscillation or rotation. To wrap up, I want you to try applying what we have learned to these review problems, which connect our new derivative rules to physical motion. For the first question, a good strategy is to rewrite the cotangent of x as the fraction cosine of x over sine of x, and then apply the quotient rule. The second problem gives you a position function, s of t equals 2 minus 2 sine of t. To find the velocity and acceleration, you will need to find the first and second derivatives of this function with respect to time. For the last part, remember that an object is momentarily at rest when its velocity is exactly 0. This means you should set your velocity equation equal to 0 and solve for the time t. Working through these examples is an excellent way to solidify the link between the abstract rules of calculus and their concrete applications.